Alright, I said I'd do a video, so trying to keep my promise, but I feel like, hot garbage, I think is what people say. Hot garbage is how I feel. So be careful. I'm probably going to make some mistakes and stuff, but we'll do this anyway. Um, let's start with 25 because, it's the first one. I'm not going to do all of these, though, because they're all pretty similar. But starting with 25. If you had parametric equations and you wanted to sketch their graph, then ideally you would know some stuff about them. Like, for example, if the x equation is linear and the y equation is also linear, then you're pretty obviously going to get a line. And if you're going to get a line, then all you really need to do to graph it is just plot a couple of points. So just build a t-chart. T-chart being the T shape that makes your X's and Y's, but it also has T in it. And the easiest things to evaluate would be like 0 and 1. So plugging in 0 gives 3 and 4. So you pass through the point 3, 4. 1 is negative 2. And 1 gives 7. So just plot those points. And then you know that your graph is just the line that connects those. Nah, good enough. Close enough, right? All right. So from here, we could go do 26, but hopefully you can tell that 26 is going to be the same deal. It's another linear and a linear, so it's a line. But the difference would be that they gave you a parameter interval, so you wouldn't get a whole infinite line, you would get a line segment. So instead of plotting just any two random points like 0 and 1, you would plot the two endpoints at negative 3 and 5. And plugging in negative 3 gives 1. And plugging in negative 3 gives 7. Plugging in 5 gives 9. 5. Negative 25. Take away 8. I don't know, 33 or something. Again, I'm sick. Don't quote me on any of these numbers. Check them yourself. But basically, you would get the line segment that just lives between those 2 points. That's the difference between 25 and 26. All right, so 27 is different, but still not hugely different. For 27, you get x equals 2t squared plus 3. And you get a y that equals t minus 1. All right, so this time your x's are quadratic and your y's are linear. So you're probably thinking that the overall result will be something that looks quadratic, and you're right, it'll be a parabola. And for this one, I think it's probably best to actually go ahead and put this into rectangular form and then sketch our graph from the rectangular form. So to do that, you would add 1 to both sides and get a y plus 1 equals t. Then take that expression and plug it in here for t. So you get an x that equals 2 y plus 1 squared plus 3. And since this is x equals a y squared, you should know that this is a parabola that opens to the right. So you might want to kick this 3 over to the other side. And then leave your answer in this form. This is our sort of conic section form for a parabola. It tells us that we have our vertex at 3, negative 1, which is right here on our grid. And then from here we could just plug in to find a couple more points. So what's the best way? I don't know. Oops. I mean, you could evaluate the original parametrics if you wanted to. It should be sort of obvious that if we let t be 0, I would get 3, -1, which is my vertex. Although I wouldn't think that your vertex always has to be associated with the t value of 0. It wouldn't always be, but at this time it is. So maybe it's easy from here to just let t now be 1, -1, 2, 3, whatever. But I think since we've got a rectangular, I might just deal with that one. So we've got x, y. Nah, you can't see any of this. Yeah, that'll do. Okay, so now if you were going to evaluate, then we're plugging in down here. So I think I'd make up y values, and the obvious y value to choose would be 0. And if you let y be 0, you get 1 squared is 1 times 2 is 2, add 3, you get 5. So 5, 0 is a point. And then from there, you could just reflect that over your axis of symmetry. And you know you get another point down here. And I think 3 points is plenty. We know that we open to the right, so we know our axis of symmetry is horizontal. There's your graph. We know that this is t equals 0. Yeah. And as far as which direction are we going, well, we're definitely going right. Looking at these y values, this is an increasing slope. So we can see that as t gets bigger, the y's are getting bigger. So we're definitely going up, up, up this branch. And then we'll probably come back in along this one. But there you go. There's your t value of 0 and your direction of growth. Okay, we should definitely do 28. Although 28 is probably a piece of cake. I'd like to think by now that most of you guys just have it memorized, that this is going to be a circle, because it's cosine sine, the coefficients are equal, this thing's a circle. There's technically a +0 and a +0. Those numbers on the end give you your center. So we're centered at the origin, and then the coefficient is our radius. So just go up 3, down 3, left 3, right 3. So the only thing now, something that's been a bit of a sticking point for a lot of people, which is finding a starting point and direction of rotation. But I still hope that you're just able to do that from the parametrics. Think about it. If x is being given by this cosine equation, just sketch the graph of that cosine equation. It's going to start up here at its max of 3 and go bzzz. And the sine equation is going to start at 0 and go up to a max of 3. Bzzz. So we can see that times 0 is just these y-intercepts. It's 3, 0. So this point here is our starting point. And then moreover, we can see from the x equation that the x's are getting smaller, which we knew that anyway, because from this point we had to go left. There was no other choice. But we can see from our sine equation that from this starting point we go up. So the y's have to be increasing. So that means from this point I have to go up. I have to go counterclockwise. So there's your starting point and your direction of rotation. We go around counterclockwise. Okay, so 29. Okay, so for this, I would definitely put this into rectangular form. It says right down here that e to the t is equal to y. So I can definitely make a substitution here because I know that e to the 2t, well, e to the 2t is just e to the t squared. And so as soon as I make that little algebraic change and rewrite e to the 2t as e to the t squared, then I know I can just take y and substitute it in for e to the t. You don't always have to make a direct substitution for t. You can substitute in for any expression as long as they're equal. So I can replace e to the t and it works just as well. So that gives me an x that equals y squared minus 1, which I can tell is another parabola. I can tell it's another parabola that opens to the right. I would add 1 just to kick it to the other side. And then again, from this conic section form, I can see that my vertex is -1, 0, and I know I open to the right. Okay, so let's plot some more points. Let's see what point is assigned to t0. If you plug in 0, you get e to the 0, which is 1 minus 1 is 0. And if you plug in 0, you get 1. So notice that our vertex this time definitely is not the point that's associated with a t of 0. t0, for whatever reason, is this point. And now that I have that point, I could just bounce it down. Again, just using the symmetry of a parabola that opens to the right, I can just bounce all these points. So that's 2. I could let x be 1, but that's going to give me what? E squared minus 1. I don't feel like messing with an e squared minus 1. So I guess the best choice is let this be a half. And then you get e to the 1. No, that's still e. I don't know if there's any other points that come out very great. You know what? Let's just call it then. Because I did say 3 points was enough anyway. So just show me a parabola opening to the right. Alright though, what's my direction of growth? Well, again, if the x's are being given by e, well, I don't want the x's though, I want the y's. If the y's are being given by e to the t, well, the graph of e to the t had a horizontal asymptote, hopefully you remember, and then it grows. So for sure, we're talking about starting here with y values that grow. So there it is. We start here and we grow. So we're running to the right on this one. And that's it. And then 30. I could probably safely say that you don't need to do 30. But should we try it anyway? Nah, let's just not try it. Alright, so moving on. Alright, so let's do these. These should be pretty straightforward too, because this is really just a strict formula. If you're trying to write the parametrization for a line, these aren't really curves, they're just lines. Now technically we use curve generically to mean any shaped graph. But if we're doing a line, then my advice was start by writing a vector equation. Because that vector equation will always be of the form xy equals any point on the line. So P1, P2 is any point on the line. Then you add to that some direction vector, V1, V2. And so this was any vector parallel to the line, and this was any point that's on the line. So if you're trying to pass through these points, then if I were you, I would probably just pick that point. It doesn't have any negative signs in it. So 3, 4. Then for a vector, I would pick the vector that goes from 3, 4 back to the other one. Would I? Yeah, sure. Why not? We can do that. So from 3 to -1 is a change of -4. And from 4 to -2 is a change of -6. times t. And technically you're done right now. But if you wanted to kind of simplify, you could, because we said this vector just had to be any vector parallel. So if you sort of factored out like a -2, then you could just use +2, +3, and that would still model the exact same line. But this gives me cleaner values, right? So from here now, I just turn this into parametrics. And I know that my parametrics will be that x equals the x coordinate of one of my points, which is 3, plus the x component of my direction vector, which is essentially my slope vector, so it'll be plus 2t, and then y equals 4 plus 3t. And they did say that we're supposed to be parametrizing the whole entire line. So for this, we're done, okay? But because I've kind of messed around with this one, because I started at the second point, because I used the vector that went from B to A, and I changed it around, let's play a little game. Or if that was A and this was B, how do you turn this into the parameterization of segment AB? Well, hopefully it's clear that we started at B, so times 0 is the one that gives B, right? So one of these ends has to be 0. But I started with a vector that went from B towards A, but then we reversed it because we factored out a negative. So the vector that we're using goes from B away from A. So we need negative numbers to push us back towards A. So 0 will actually be our max. Now I also chopped this vector in half. So to get all the way to A, I would need 2 of those vectors. So A would be associated with -2, and B would be associated with 0. So if I just added this parameter interval to this parameterization, then I would be getting segment AB instead of line AB. And hopefully that makes sense. Okay, let's do 32. So for 32, I'll do it the more normal way for a segment. So for 32, my advice to you is if you're trying to parameterize a segment, then go ahead and just let one be A and one be B. And just make sure to use A as your point. And then make sure to use segment, or be sure to use ray AB as your ray. Because, ray AB, yikes. Alright, I need to go to bed soon. Use point A for sure as your starting point. And then use the vector that goes from A to B. Because we said when you set it up like this, your parameter interval will always just start from 0 and go to 1. And you can just take that to the bank. It'll always be that way. So if I set it up like that, then my x equation would be the x coordinate of A, which is -2, plus the x component of my vector, and it looks like I'm running 7 to the right, so 7t. And then y would equal the x coordinate of A, which is 3, plus, I think I said that wrong again, but y is going to be the y coordinate, which is 3. And then the y component, which is bringing us down 4, so -4t. So get rid of the plus. Minus 4t. And then attach the right interval. So we'll say t is an element of the set that goes from 0 to 1. And now that parameterization is guaranteed to give you only the line segment that goes from A to B. Okay. Yeah. So I don't think it's smart for me just to leave this behind. I think if we're talking about this, let's jump. We're not going to start talking about parametrics. Let's jump past this to this last batch of problems that's talking about parameterizing curves again and run through those. I'd like to think I don't have to do 27 again because it's exactly like the one I just did. I don't have to do 28 either, but something like 29 is different. It says we want to parameterize the lower half of the parabola, blah, blah, blah. All right, how do I do that? Well, if this is my rectangular equation, which it is, then basically what you'll do is just say, since you've already got one equation on the left that's entirely in terms of x, and one equation on the right that's entirely in terms of y, you could just say, well, why don't I let x minus 1 equal t? And why don't I let y squared equal t? So it's almost like you're just taking a second equation where t equals t, and then you're substituting in. This t becomes x minus 1, and this t becomes y squared. Oops, I'm doing this backwards, sorry. What I meant to say, of course, was you now can write an equation where the x minus 1 is equal to the t, because the left side has to equal the left side, the right side has to equal the y side. So you can also say y squared equals t. And then that's it. These are now parametric equations, but you'd probably want to see them solved for x and y. So your x equation would be x equals t plus 1. And your y equation would be y equals plus or minus the square root of t. So that's your parametrization. But without placing any limits on t, you're getting the whole entire parabola. And it says here that we only want the lower half. So it turns out that restricting t will never give me the lower half, because the way this thing is plotting itself, if you think about it, is x, y. If you let t be 0, then when you plug in, x gives you 1, of course. And when you plug in 0, you just get 0. Positive 0 and negative 0 are both 0. So your vertex is 1, 0. But if you plug in 1, then you get 1 plus 1 is 2. But when you plug in 1, you get plus or minus the square root of 1. So you're getting both a 1 and a negative 1. So the same t value is generating two outputs. So if I go over to 2, I'm getting positive 1 and negative 1. So it's not like I can get the top half by just saying that t has to be greater than 0. That won't do it, because the positive t's are giving me the top half and the bottom half at the same time anyway. So actually what you have to do is modify the equation. You have to just take away the plus or minus. If I only want the lower half, then I don't want the positive. I only want the negative t values, or I only want the negative y values. So you just have to make that change and define it that way. And then those parametric equations are fine. Technically, you wouldn't even need to put any restrictions on t at all, although negative t's are going to be imaginary anyway, so you might want to say that we should just go ahead and let t be greater than or equal to 0. That way you're not plugging in any values of t that don't work. So there. Okay, let's do it again. So this time they want the left half of the parabola y equals x squared plus 2x. Alright, I think we can just do the same trick again, because this left-hand side only involves y, and this right-hand side only involves x. So we can definitely just say that x squared plus 2x equals t. Oh, geez, maybe I take that back. And we can say that y equals t. Alright, I take it back, because I don't think we can clean up this x equation very nicely. Because if we tried to clean this up, we would what? Factor out an x? I don't know that we want to be solved for x here. Ugh. Alright, I'm going to teach you something new. And probably this doesn't matter for the test, but here we go. Somebody remembers completing the square, I hope. So completing the square is when you add on a third term. so that this quadratic is factorable down to a perfect square. And we said you take this 2, you chop it in half, and you square it. So half of 2 is 1, 1 squared is 1. So if I added 1, then this thing would now be the perfect square, x plus 1 all squared. But if you want to add 1 to the right, of course you have to add 1 to the left. So now you have y plus 1. Okay. But the good news is, now that I have this in this form, I could go ahead and just let the y plus 1 equal t. I could let the x plus 1 squared equal t, and I'll get better looking parametric equations. So if y plus 1 equals t, then y equals t minus 1. I didn't leave any room for my x's. And the x stuff, if x plus 1 squared equals t, then that would mean what? That x plus 1 equals plus or minus root t, and would take 1 away from that. So x is going to equal plus or minus root t minus 1. Yeah. So there's a possible parameterization. It's not the only possible parameterization, but it's the one I'm going with. Alright, so what would this thing look like? Just plot some points, let t be 0, and you get 0 minus 1, so negative 1. You get 0 minus 1, so negative 1. Hold on. I'm sick. So I forgot that I had all these grids. Alright, hopefully you can see that a lot better. But it looks like we're getting a point at negative 1, 1, negative 1, negative 1. Then if you let t be 1, you get plus or minus 1, minus 1. And plus 1 minus 1 is 0. But negative 1 minus 1 is negative 2. So we're getting 2 outputs, and 1 minus 1 is always 0. So we got 2 ordered pairs again. We got 0, 0, and we got negative 2, 0, which is definitely showing me that we are a parabola that opens up, because we've got these 2 points, one to the right, one to the left. So we're going to open up. And of course we knew we opened up anyway, because look at the rectangular equation. It's just y equals x squared plus 2x, which we already said could factor down to x times x plus 2, which definitely shows me that my zeros are 0 and negative 2. 0 at 0, 0 at negative 2. So all of this bears out. So the answers I'm getting from my parameterization, they match what I would have expected to get from my rectangular equation. So everything here feels good. And again, the only deal is I want the left half. So it's the same thing as the last problem. The left half is generated by the negative root. The positive root is pushing us to the right-hand side. So again, if you just take away the positive root and use only the negative root, then you're good to go again. You'll only get the left-hand side. And we'll lose that point. So there, and again, you don't have to mess with t, because again, the positive t values are generating the left and right-hand side of the graph at the same time. Okay. Sure, we can do 31. We won't need that. So this time they're asking for the ray. They're saying that a ray and a half line are the same thing, which I don't think I agree with. I told you guys that a ray has an endpoint and goes forever, and that a half line has an endpoint that's open and goes forever. So I'm just going to scratch out the half line part. We'll model the ray. Now it's got to have the initial point this, it's got to pass through there. So we're doing the same thing as before. Just let this be A, let this be B. And if you have to start at A, then use A in your vector equation. And if you have to go in the direction of B, then make sure you use the vector that starts at A and goes through B. So use vector AB as your vector. But if you think about this vector equation, then that's going to give you the perfect parametrization. So x is going to be the x coordinate of A, which is 2, plus the x component of the vector AB, which has me going left by 3, so it'll be minus 3t. And then y equals the y coordinate, which is 3. And then we're going left 4, so minus 4t. So there's my parametrization. Now that's the parametrization of the whole entire line. They want to start at A and go through B. So we're just going to let t be greater than 0, because 0 starts us on A, and then there's a B out here, and we're using a vector that points toward B. So any positive value of t is going to push me out to the right side of B, and we'll get that whole ray. So that's your parametrization for 31. And I don't see any difference between 32, so we'll skip it. Okay, so let's go back. Yeah, sure. Let's do these now. Alright, I don't know how many of these I'm going to do, because these are similar to the other things. But we'll certainly do the secant tangent ones and the whatever else is kind of weird. Whatever other ones we haven't had a lot of practice with, I'll try to go through. Alright, so something like 15, I would like to think you don't need any help with. But I'm going to do it anyway, I guess, just because it's a good starting point. Ugh, my ears are ringing. Okay, so 15. So 15 says that x equals t, and that y equals root t. So it should be pretty obvious that if you just square both sides here, you get a y squared that equals t. And if x equals t and y squared equals t, then x equals y squared. And that's a parabola. It's a parabola that opens to the side. It's a parabola whose vertex is at 0, 0, and that passes through the point 1, 1, and 1, negative 1, and that opens to the side. And maybe I'm doing all that too fast, but hopefully not. But again, they said that t has to be only greater than 0. So does that change things? Does that mean I only get the top half or the bottom half? Well, let's take a look. In my original parametrization, they said that x was t, and that y was root t. So if you let t be 0, whoopsies. Can you guys see everything? Yeah. So if you let t be 0, x is 0, and y is 0, you get the origin, which we probably knew. That's t equals 0. Then if you let t be 1, x is obviously 1, and y is 1. If you let it be, let's just go all the way out to 4. X is 4 and y is 2. So actually what it turns out is I lied when I said that we were getting a parabola here. It looks like we're going to get a parabola, But based on our original parameterization, we actually have restrictions on our domain and range because the y equation is root t. And if you graph root t, that is essentially only the top half of a parabola, right? It's a radical function that only has positive outputs. So even though our rectangular equation looks like it would give us a whole parabola, it doesn't, because there's no way to get those negative outputs. So we're actually only getting the top half of a parabola, or just a radical function. Of course it's just a radical function. And that doesn't really matter whether we allowed t to be negative anyway, because if we let t be negative, we would have had imaginary outputs anyhow. So that's 15. And pretty obviously we're starting at the origin and growing that away. Oops. Starting at the origin, growing this way. That's 15. Okay, 16. All right. Hopefully as you look at this, you know that we're going to use the identity that secant squared minus tan squared equals 1. And we want to isolate the trig functions before we do that. So you'll add 1 to both sides to get x plus 1 equals secant squared. And then you'll square both sides of the y equation to get a y squared that equals tan squared. Now you'll subtract. And as long as you subtract in the order of secant minus tan, you'll get 1. And if we're subtracting in that order, then we're doing x plus 1 minus y squared. And that equals 1. Which looks like it's giving us a parabola. So I'd subtract 1 from both sides, and they cancel. I would add y to both sides, and I get y squared. Yeah, sure. Okay. So what's that going to be? That's my parameterization. So shouldn't that be a parabola whose vertex is 0, 0? And because it's y squared, we'll open to the right. And if we go over 1, we'll go up 1, over 1, down 1. So again, I'm being a little bit careless here. I'm just graphing the whole thing, but wait. If we go back, we're defined parametrically, right? So we probably inherit some restrictions from these parametrically defined functions, but moreover, there's also restrictions on t. So we may have even more restrictions based on the fact that t can only go between negative pi over 2 to pi over 2. So again, you should probably consider the graphs of these functions. So secant of t squared, or secant squared minus 1, you know what, forget that guy. That guy's hard to think about. And I did say in class that often, as long as you get the restrictions from one equation, you won't have to worry about other restrictions from the other equation. So let's see if that plays out. So the good news is negative pi over 2 to pi over 2. That kind of just means that we're limiting the tangent equation to just that first period, which says that we do get every possible y value. So that makes me think that maybe I don't need any restrictions here, because I'm seeing a parabola that covers every possible y. This tan equation is going to give me every possible y value, meaning it does have a range of all reals. Even with the restricted t interval, it still has a range of all reals. So what about this secant squared thing though? The minus 1 would put your midline down here at negative 1, which would put your max up here at 0, and your min down here at negative 2. And normally I would say that we get one sort of uppy branch, then we get another downy branch, but we're squared, right? And the fact that we're squared means that you're going to get an uppy branch and then another uppy branch, because all these negative outputs get squared and they're positive. Yeah, so you get an uppy branch, uppy branch, uppy branch. But if you look at that, all that's telling us is that this guy's range, which again, it's tricky, but the range is the x values, right? So all the x's come from this thing's range, and this thing's range is 0 to infinity. And guess what? For our parabola, that's 0 to infinity. So this was kind of a weird one. You might have thought that defining this parabola in terms of secant and tangent would cause domain restrictions, but it didn't. You might think that limiting your t values to some t interval would cause domain or range restrictions, but it didn't. We really do just get this entire parabola. And what's happening at time 0? At 0, we're 0, 0. So the vertex really is 0, 0. And as that increases, the x's increase, the y's increase, so the x's and y's have us going that way. So there's your graph for 16. Let's try 17. Okay. All right. So here we've got a negative secant. We've got a tan. We definitely want to square both sides again to get to secant squared. If I square both sides, this will square, and the negative will cancel out. This will square, this will square. And now I can subtract. So I get an x squared minus a y squared. That equals 1. And hopefully you recognize this as a hyperbola. Let me get a grid for this so it's not stupid. Okay. So for this hyperbola, we can see that we'll be centered at the origin. We can see that we've got denominators of 1 and 1, which means we're just going to go left 1, right 1, and we're going to get a little reference rectangle that's just a little 2 by 2 square. And that will mean that we get asymptotes with slopes of -1 and 1. And we know that our branches are going to open, let's see, x comes first, so we'll open in the x direction, which is left to right. So you should be expecting a hyperbola that has a vertex here at 1, 0, and that opens to the right. And just make sure you stay hugging that asymptote closely. Another one at -1. Alright, and again, I'm doing this on purpose. I'm sketching more than I should. Probably, because if our original definition was from these parametric equations, then are we going to inherit domain restrictions? And the answer is maybe. It says x equals negative secant t. It says y equals tan t. So I don't think either of those will give us domain restrictions, because we know that secant t just lives, what, above 1 and below -1. Now they did say negative secant, so that's going to reflect us. But we're still getting all x's that are less than -1, which makes sense. I can see I'm getting x's left of -1. and I see I'm also getting x's to the right of -1. So my domain actually jibes with the range of negative secant. And for tan, same old tan. Tan maps onto all real numbers, and I do see that each branch here maps onto all real numbers. So I don't have to artificially slice away any part of this graph unless these intervals matter, which they don't, or do they? Let's see. For tan, they said that we're restricted from -pi/2 to pi/2. So for tan, I still get outputs of all reals, right? But if I'm restricted from -pi/2 to pi/2 over here, then that's only half of a cycle. I only get these negative values. I actually am barred from getting any of these positive values. So that means I'm actually going to lose my right-hand side because of the interval, the t interval. So there. The graph of 17 is actually just the left-hand side of my hyperbola. And then I think there's probably a little bit more to this, where if we were going to do our direction of growth, then our initial point is probably that vertex, right? If you plug in 0, negative secant gives -1, and tangent gives 0. So -1, 0 is definitely my starting point. But because the x's are defined by negative secant, what does that mean for us? It means the x's start by decreasing, which made sense. We knew that they would decrease. And the y's start by doing what? The y's increase. All right, so the fact that we're negative secant doesn't really change much. The negative secant is what made us get the left-hand side instead of the right-hand side. So we'll start here, and we will still run up the branch at first, not down the branch, up the branch. But there you go. So you can see how this time we did get restrictions. The restrictions did not come from the parametric equations. They came from the perimeter interval. I don't want to do 18. 18 seems really similar. 19 looks similar. 20, 21, 22, 23. Did I do everything they're telling us to do? Yeah. Okay. Maybe I'll do 23 just because it looks pretty easy. Some of y'all might be freaked out by the radicals, but you shouldn't be. Okay. So this is real easy because, again, you don't have to solve for t to make a substitution. If it says that y equals root t, then you can plug right into the root t and just get x equals 4 minus y. And then you're already done. There's your Cartesian equation. Or your Cartesian equation is the same as your rectangular equation. So what do I do from here? I would add y, subtract x. We get y equals negative x plus 4, which is just a line. But are we going to inherit any restrictions? Well, yes, we certainly are. Because you would think this line hits the y-intercept at 4 and has a slope of -1. So you'd think that this line has a domain and range of all real numbers. But of course, that's not true. Because if you look at the parametric definition, for the x equation, you have 4 minus root t, which is negative root t plus 4, which means we've been slid up 4. And then we've got this negative sign that would flip us upside down. So it would look like a radical function that got flipped upside down. So we can see that the set of all possible x's would be this function's outputs, which would be that the x's have to be strictly less than or equal to 4. So where's 4? 4 would be this x-intercept over here. It says the x's have to be less than that. So that means everybody to the right-hand side is getting chopped off. Oops. So all that stuff is gone. So what we actually have is array. Now what about the y equation? Does the y equation give us more restrictions, or does it just sort of agree? I think it just agrees, because it usually does. But it says y is root t. So that means we start at 0 and we follow the radical function's behavior, which says that my y values can only be those values greater than 0. Which would definitely say that, okay, here's 0, I can only be bigger than that. So this is it. Instead of actually getting a line, we just get this ray. But they said they wanted a Cartesian equation. Here's your Cartesian equation. If you wanted to make this Cartesian equation work, you'd have to put a restriction on it that said x has to be less than or equal to 4. And then you would get only the ray. It says what portion of the graph or Cartesian equation is traced by the parametrized curve. So you would say only the portion of the line that's above the x-axis. You could describe it that way. Anything else to say here? I don't think so. Well, direction of growth, all that good stuff. Let's do that. Alright, so whatever. T, x, y. If you let t be 0, then you get 4 and 0. Which is not a huge shock that the endpoint of our ray is times 0. Then, if you look at your graph, you can see the x's are decreasing, which is not a huge shock because we knew that from here we had to go left. If you look at your y equation, you can see that your y's are increasing, which is not a huge shock because the only direction for us to go is left and up. So the fact that the x's are decreasing tells me I'm definitely going left. The fact that the y's are increasing tells me I'm going up. So here's times 0, and I'm plotting that way from right to left. Okay. Okay. Excuse me. I'm super running out of steam here. Where were we? We just did 23, 24. Looks interesting enough. Let's do it. 24 says that x equals t squared. And y equals the square root of 4 minus t squared. So for sure, if I was trying to get into Cartesian coordinates or rectangular form, I'd square both sides to get a y squared that equaled 4 minus t squared. Then I would add t squared and subtract y squared to get a t squared that equaled 4 minus y squared. And it's at this point that I can certainly notice that if x equals t squared, and there's a t squared down here, I can just directly substitute x in for that. So you get x equals 4 minus y squared, which is not really in the proper form. We would want a positive y squared. So honestly, you would subtract 4 from both sides, really, because we want the x on the left-hand side and the y squared on this side. And probably I would let this stay negative, because if we're doing x minus h equals 4p y minus k squared, then that negative just means our p-value is negative. So this is sort of the right form, to leave the negative on the y. And then what we know about this is it's a parabola that opens left. So for the very first time ever, we're seeing a parabola that opens to the left. Okay? And what else do we know? We know that the vertex is 4, 0. So let's plot it. So vertex goes there. And then find a few more points, either by evaluating your rectangular equation or by evaluating your parametrics. I don't really care which way you do it. I'm going to try the parametrics. 0 gives me 0, and 0 gives me, trouble. No trouble. That's 2. 0, 2. Alright, and we said we open left, right? I'm not liking this. I'm feeling like something's wrong here. 0 gives 0. Okay, I don't know. I'm going to keep going for a second. 1. 1 gives me 1. Oh, I didn't want 1. JK. 1 would give me an ugly number. Let's actually do 2. Which gives me 4. And then 4 minus 4 is 0. So there's that point. Okay, well, whatever. I was about to say something about how I do believe this is our vertex and we would open to the left, but we're not going to get the whole graph anyway because we have this parameter interval that only goes from 0 to 2, and I just plotted all the points from 0 to 2, right? So we should get this as our vertex. We should open this way, so I should see a graph that's sort of concave down. I'm not going to get the bottom half though because of the way we're defined parametrically. This y equation doesn't generate negative outputs, right? You're not going to get that bottom half. As we solved algebraically, we never got like a plus or minus thing. We never took a square root to get a plus or minus. So you should be expecting to only get the top half. And then the thing that's a little weird, I suppose, boy. Come on. Alright, so the thing that's a little weird is our times 0, I think, is not our vertex over here. It's just this random point. And we build out to in that direction. But that's all you're getting. It's just that little piece of a parabola. And that's that. Alright, 25 is weird because you've got t and 2t. So I'm not going to go into this. Maybe we could use our double angle identities to try to find a way to get to Cartesian form. But I don't care, and it's not going to be on the quiz, so forget it. 26 looks pretty straightforward to me, but we do have a parameter interval. So I'll go ahead and do 26 to make sure everybody's totally understanding how these parameter intervals can shape our graphs. So if we've got an x that equals t squared minus 3 and a y that just equals t, then we sort of have the world's easiest eliminating of the parameter. We just take y, sub it right in, and we get an x that equals y squared minus 3. We add 3 to both sides to get an x plus 3 that equals y squared. And we see that what we've got is a parabola that opens to the right. And its vertex would be negative 3, 0. And then from there, if you let, let's do the parametrics. I still think that's best. So what do you get when t is 0? You get negative 3, 0. Which is no big surprise that our vertex is associated with time 0. Now it does say the t's have to be positive. So if I go to 1 now, then I'm getting 1 minus 3 is negative 2, and 1. If I go to 2, I get 1, 2. Okay, so I think we can see that as the t's are getting bigger, I'm plotting only the top half of the parabola. And the bottom half would have been plotted only by the negative t values. And since we're not allowed to use negative t values, we're not going to get our bottom half. So based on the way we're parametrized here, we can see that the y equation equaling t means that we get positive y's for positive t's and negative y's for negative t's, but negative t's are not allowed. So we're only getting the top half of a parabola. And we're growing in that direction. So there you go. Alright, so that's it for parametrizing stuff. This video is already over an hour, so I think I'll make a second video that goes over projectile motion stuff. So you guys can check that out later.